Cannot hear me? Okay, maybe I'll just hold this. Okay, so, let me put it down. Okay, so I'll just share some of our recent work and thoughts on state representation learning.
It's not that. This is I turned this off. There we go.
Okay, thank you. Okay. Okay, so first, what is state representation? As a theoretician, we first introduce a notation. So we want a state representation map. So the basic idea is, okay, so my states can be very unstructured. My states can be raw pixel images, or my states can be even text or languages. So our goal is we want to find a mapping per se that maps a raw state into a vector. So we have a numerical representation. And in the world of deep RL, we can just think about state representation as, so we feed the raw state as input to neural network. And then we read maybe the last hidden layer. And that's the representation learned by the neural network. And so what do we need about state representations? So first, so if we do have good state representations, then basically maybe like in this DQN paper like a few years ago, we can actually visualize the state space in low dimensions after the state representation map. And also, hopefully, that the dimension of state representation is actually going to be important. The dimension of state representation is going to actually determine the complexity of learning an optimal policy or learning an absolute optimal policy. And having a good state representation is going to make it easy to generalize from what have been seen before to future decisions. And also, state representation is very important for exploration and having a small regret in online RL. Okay, so as a theoretician, so I'm going to just discuss with you about so what do we want for a good state representation or state embedding. So first, a lot of results in RL theory are built on having some feature representation of state space, or maybe state space and action space. So typically, we want to have our precise mapping to give us a number of feature functions or basis functions. And sometimes we want to use those basis functions to parameterize and represent high-dimensional value functions using a linear model in the simplest case. And a strongly related notion is if I want my psi to be able to represent every possible value function for every possible policy and every possible reward, then this essentially is saying that we need the state representation mapping psi to be able to represent the entire environment, the entire transition kernel. And in this sense, basically, the underlying assumption is the transition kernel can be represented using the psi mapping according to a linear model. And this is also known as the factor model of MDP, as Chava mentioned this morning. So basically, so if we do have such a psi, so how does it help us? So basically, we are able to reduce the space of all possible value functions to a smaller dimensional space. And by using such a perfect psi, then it's possible to actually reduce the minimax sample complexity for estimating an absolute optimal policy and under a generative model. So we had a result like a year ago basically saying that, okay, if I have perfect state feature map psi, and also we can also have another perfect action feature map, then it's possible to design an algorithm to take advantages of all the structures of MDP and to reduce this non-improvable sample complexity in the tabular case to something pretty small, to something very small and linear in the dimension of the representation space. So this is one motivation to have good state representations. Another motivation is, okay, instead of sample complexity, sometimes we care about how to explore and how to learn on the fly. So again, suppose that we already have this perfect sorry, I think I changed my notation a little bit. Suppose that we have this feature map phi that maps the joint pair of state action to a vector. If I have state-only feature and action-only feature, we can take their outer product, and then we have a matrix, and then we can vectorize it and get this phi. Okay, so suppose that we are in the world in which the dynamics can actually be represented using the current feature map or embedding map. In this case, we can do Q-learning pretty easily. So whenever we want to estimate Q value, in order to encourage exploration, we always want to be optimistic, right? This is the key message from bandit theory. So in this case, because we do know that the underlying dynamics can be roughly represented by something low dimensional, then all the computation and all the high dimensional functions that we hope to estimate should also be able to estimate it in low dimensional space. Then basically the algorithm is going to be roughly like this. Suppose that we want to do Q updates or just value update or Q learning. So instead of doing in a tabular way, so really what we want to do is whenever we try to estimate the inner product between the transition kernel and the high dimensional value function, we know that this is really not high dimensional. So we can actually do regression here. I have approximation here because there are many ways to do regression. So some way of linear regression there. And then we use this phi feature map to decode from the low dimensional vector W hat to actually obtain what we care about, this particular state action pair. And on top of it, we want to encourage exploration. And it turns out that the natural bonus function is going to be exactly this. We just look at the precision matrix corresponding to all the state action feature map that we have seen so far. And then we try to look at the current level of uncertainty along this vector of feature map corresponding to the current state action pair. Okay, so this is very much like linear bandit, but it turns out that this approach already works, and one can actually prove that this particular method is going to have a regret bound that is independent of the total number of states. And instead, the dimension is really just a dimension of state action space. Okay, so another motivation is if we have the good psi, then we can reduce super high regret into something small because we are able to generalize knowledge more easily and we are able to explore faster. Okay, a third motivation is, okay, so maybe the linear factorization model is too strong. So what if let's get rid of this linear model? What if the only thing my state embedding psi provides is now we map our raw states into a vector space. And now I have a notion of Euclidean distance in the space of state embeddings. So what if the only knowledge I have is this distance or metric is somewhat useful? Let's consider a very simple case study. We just have a deterministic system, nonlinear. We don't know the transition function at all, but we can learn about it. And the only assumption we're willing to make is, I know that somehow I have a metric and my system is going to be smooth or Lipschitz continuous with respect to the metric. Okay, so what can we do here with just a little bit of metric information? And again, we can do optimistic Q-learning. And in this case, we do not really have linear models, so we cannot do regression to do estimation. But we can just do something super simple. With only a metric, the only thing we can do is nearest neighbor search. So we can just look at all the neighbors in the past experiences and find the best neighbor with the tightest upper bounds. And again, we are going to use the metric, this distance function, as a novelty bonus function to encourage exploration. And this is fully non-parametric, and one can show that this algorithm actually achieves near optimal minimax regret. And this regret depends on the doubling dimension of the state space and the diameter of the state space. So what's interesting is, so the doubling dimension of state space is actually not the dimension that we think in the raw data form. For example, if we think about images of a computer game, so the images can be like of dimension, for example, like 200 by 200. But however, the images are going to be generated by some computer program with fewer internal parameters. So if we think about the manifold of all the states, this manifold is likely to have a much smaller intrinsic dimension, which is this doubling dimension here. So basically, the observed dimension doesn't matter. And this algorithm is really going to do non-parametric manifold learning while doing Bellman equation solving. Okay. So basically, the theoretical motivation is we maybe hope to have a good metric so that the diameter and doubling dimension is something reasonable and not too big. Okay. So now, let's think about, we want to learn state representations. We want to find this psi. So what should be some good principles for evaluating whether the psi is good or not? So first, we say that, okay, if we want to use linear models, if we want to have a big win in dimension reduction, then hopefully we want psi to be able to linearly represent value functions, or even linearly represent this entire environment, the transition kernel P. And also, we mentioned that in this case, the sample complexity and the regret are going to depend linearly on dimension of psi. And then we want psi to have a small dimension, of course. And another way of thinking about this is, so we are mapping state to a vector. So we want these vectors to still preserve information about the state, so we can make the same level of decisions. So in this sense, we can think about that the metric provided by psi is telling me whether a new state is novel or not. So by novel, we mean that a new state could be a new image that we haven't seen. But this state is only going to be novel if it's going to lead on to a new path in the game that we haven't really played before. So in this sense, we can think about that we want to be able to find psi such that the distance between state embeddings after we apply this psi mapping is going to be in some way related to the discrepancy between conditional transition densities starting from the two states. And I put a question mark here because we don't know what is the best norm to use. Okay. And if we look at all this criterion, and we think about the very simplest case of just tabular Markov chain, and we can even just put this maybe just an L2 norm for simplicity. So really, the best answer is just to estimate the factorization of the transition kernel P in the very simple case. Okay, so that's what we try to do. So we spend some time on trying to understand what is the minimax optimal estimation of the factorization of a Markov chain from trajectory data. And we proved a bunch of upper bounds and lower bounds. We also proved bounds on the expressibility of the feature space of the spectral functions that we learned through estimation. And luckily, we can actually make some upper and lower bounds match. So I think in the tabular case, this question is not super hard. And next, okay, tabular case is easy because really it's about factorization of matrices. And now what if, okay, we just look at a state transition trajectory, but my states are no longer discrete valued. So now we really care about this continuous transition kernel, and we want to factorize it. So the question is, okay, is it possible to learn the state embedding function psi? Hopefully that the span of this psi is approximately equal to the span of the left singular functions of the transition kernel. Okay, so we proposed one solution. And so because we cannot really we can never deal with multivariate data without any structural assumption and without suffering from the curse of dimensionality. So let's make things a little bit simpler and say that, okay, what if I have something to begin with? We try to understand factorization and state embedding of a Markov chain in a kernel space. And we know the kernel function. Okay. So again, my goal is that I want to find a psi in order to preserve some notion of distance between transition distributions. And the solution is very simple. It's really about factorization. So we can begin with a kernel space. So if we only have a kernel space, it could be infinite dimensional, but we can approximate it easily by generating random features. So essentially, we can generate a large number of random features. So we are lifting the space to high dimensional. And then we know that we want to look for simpler low dimensional principal functions. And on top of that, we can try to estimate a projection or an embedding of the unknown transition kernel onto our feature space. And then we can apply some version of low rank approximation. And in the end, so we can get this embedding map, which is the product between the random feature map, which is high dimensional, and this compression matrix we obtain through low rank approximation. Okay, so now what we can prove. So this approach can be thought about as trying to kernelize the diffusion map in a way to reduce dimensionality. So we are inspired by studies in molecular dynamics, and we can do it in a kernelized way. So we define the kernelized diffusion distance by comparing two conditional transition density functions, and then we look at the Hilbert space norm of their difference. Okay, and that Hilbert space really defines all the functions and the quantities of the states that we are interested to predict. Okay, and we can show that actually, so this kernelized state embedding approach preserves diffusion distance with some additive error. And one can analyze that additive error and show that this additive error relates to, for example, like an approximate rank, condition number, and a few other quantities. And turns out that this error can be quite small, meaning that it's possible to find the leading feature space that we want without looking at too many data points. Okay. So on top of this, another related question, again, coming from molecular dynamics, is the following. So in order for scientists to do fast simulation of some complex process, oftentimes they want to discretize state space, as Christina just mentioned. But however, discretization is never uniform. It's really about how can we find partition of state space such that after we lump the process onto the partition, the reduced order process still meaningful. And this turns out to be a problem known as finding the optimal metastable partition, meaning that we want to partition state space in a way that each cluster is very stable within a certain time horizon. And turns out that this optimization problem is equivalent to another optimization problem on top, which can be just solved by k-means. So the solution, again, is very simple. So our goal is, again, to cluster states with the principle to cluster states according to their similarity in transition and according to preserving metastability. And the solution is really that we first look at the data from this underlying diffusion process, we estimate the psi, and then we apply certain version of k-means. And that's it. And then we can prove strong statistical guarantee about this approach. Okay, so this is a toy example for using a stochastic diffusion process. So we made up a potential function, and on top of it, we add Gaussian noise to define a partial differential, a stochastic differential equation. Okay, and this is the invariant measure. So we try to see that, okay, from trajectories generated by this process, can we learn some structures of the state space easily? So there are the results. So the first row are really just clustering results as we change the number of clusters. As we can see, really, we can increase the granularity of clustering, and more structures of the state space is going to emerge. So basically, states in the same cluster are going to be very similar in terms of their future distribution of states, starting from those states. Okay. And we can also play with the horizon or the time scale, the time discretization of the process, and try to look for structures in very slow dynamics versus structures in faster dynamics. Okay, so next we try to use this method to analyze an example which is not so trivial. So we look at this Atari game, which is still a trivial Atari game. So this is the game in which we are trying to control this cannon to move around in order to shoot the demons that will appear randomly on top. Okay. And this is basically the approach. So remember that we were doing kernelized state embedding. So the kernel I pick is the composition between neural tangent kernel and a Gaussian kernel, which really means that we can first train an initial state embedding using neural networks, and on top of that, we can apply another layer of kernelized state embedding. And in the end, we get a reduced order state representation per se. Okay, so this is the state space. This is the t-SNE plot of state space before and after embedding. So if you're familiar with t-SNE, basically t-SNE says that if we try to look at the distribution of high-dimensional data points, and this is a way to do visualization in order to preserve pairwise distance in two-dimensional plot. Okay, so this is the representation learned by neural network, and this is what we can get after embedding. So what's interesting is, so this t-SNE plot is pretty scattered. So you know that if we just do t-SNE plot of just random Gaussian, it's going to be like a ball. So this is pretty, this is closer to a ball than this one. Okay, and then after embedding, so we should be able to reduce some dimension of distances, and this is much more clustered. And then so we try to see, okay, so what is this reduction actually doing? So we try to look for a pair of states that are very close to each other after embedding, after our embedding, but a pair of states that are far away from each other in their original form. So they are far away because neural networks or DQN does not think this circle and this circle to be similar. They are just different in terms of their state representations. Okay. So, so I found the results to be somewhat interesting. So for example, if we look at the two circles right here, so those two circles are not close to each other before embedding, meaning that their raw pixel images are actually not considered to be similar. But if we look at the two states of the game, actually they are pretty similar in terms of where the agent is. So in those two states, basically purple lasers are about to get the target, so the agents are going to score. And actually both cannons are slightly moving from right to left. So they're really moving towards similar future states or even the same future state. Okay. And also if we look at these two, so in both cases, the cannon is not doing anything, so the game is pretty much idling. But however, those two states were not considered to be similar in their original image space. But what's interesting is, so in this case, cannon is idling but moving from left to right. In this case, cannon is moving from right to left, and they are both moving toward the center. So this basically says that by using statistically proven state embedding methods, it's possible to actually identify states that do not appear similar, but states that might have similar future paths. And that's what do we mean by states, right? The states should have strategic meanings. Okay, so next. So on top of state embedding, so we try to exploit more structures. So one very commonly used latent variable model for reinforcement learning is so-called state aggregation, or it has a probabilistic version which is called soft state aggregation. It basically means that we might be observing a random walk in a high-dimensional space, but the space might be actually governed by a fewer number of latent variables, or we can call them metastates. And the observed state is going to be mapped to the latent state through aggregation distributions, and it will be disaggregated back through another distribution. So this is the soft state aggregation model. And there were many earlier papers saying that if such a model is known, then one can solve MDP in complexity which is very small. Okay, now in the tabular case. So this model is really just a non-negative matrix factorization. NMF, sorry for my typo. Okay, so can we estimate the non-negative factorization model from data? Okay, so estimating non-negative factorization has been done in many different settings, for topic model, or just for matrix completion, or for tensor models, for hidden Markov models. So there are a lot of works on this already. Okay, so we were interested in saying that, okay, statistically speaking, can we achieve the information threshold limits for estimating non-negative factorization for a probability transition matrix? Okay, so this is what we are going to do. So we start with our data, which is really state trajectories. And state trajectories, they don't have to be tabular valued, right? They can be multidimensional, because we can always map every single state in, I think I have a wrong notation here. We can map a single state through the embedding map we learned to a value or to a vector. Okay. Yeah, it should be psi hat, not u hat. Okay, so now we have seen so many states, and we can map each state to a vector. Say that my vector has dimension 3. Now this is the space of my state embeddings. Okay? And now we want to look for non-negative factorization. Non-negative factorization really means that if one state is a mixture of a few latent states, right? Then in this embedding space, it means that one point here is a convex combination of a few other latent points. And then this is entirely a geometry problem. Looking for state aggregation is really about finding convex Hall approximation. So we can just look for the vertex, and hopefully the approximate vertices can tell me something about the underlying metastate. And we borrow the name anchor from topic models. We call those states anchor states. Okay, and we prove some statistical error bounds. Okay, so this is a toy example, but I think it's quite convincing. So in this example, the data are taxi trips in New York City. So one trip gives me a state-to-state transition pair. Okay, so I have a bunch of state-to-state transition pairs, and we can use this information to estimate state embeddings and then to look at convex Hall approximations. And then we can look for anchor states that are close to vertices. So what's really interesting is those anchor states we identified match perfectly with landmarks in the New York City. So I think in a way that really we're doing decomposition of the traffic, and every single vertex that's meaningful happens to be an important landmark. I think this is related to the idea of key point that Russ was mentioning. And on top of this, we can also identify every single aggregation probability distribution, every single disaggregation probability distribution. Okay. So there are many, many theoretical questions that are open because I just tried to did the very simple first step. So first, can we learn state embeddings while doing exploration? So this is going to be a very challenging problem, and I believe John Lamford, I don't know if he's here today, he will talk about this tomorrow. Other question is, we were talking about basic linear models or very unstructured non-parametric models. And is there something in between we can leverage? Can we do better? And the third question is, even if we have good state representations, then are they sufficient? So I believe Sean will talk about this tomorrow. So there are many open questions about how to learn state embeddings and how to learn state embeddings in order to do our RL better. And this is a very interesting field of research. And finally, this is to thank my collaborators, and many of them are in the audience. Thank you very much. Emma?
This is really interesting work, and it was great to see. My concern with state representation learning is that in challenging tasks with like combination locks, by the time you learn the state representation, you would already solved the exploration task. And so I'm wondering what you would speculate about, are there going to be sweet spots where we can learn the representation fast enough to be able to benefit from it?
Yeah, great question. I think you're definitely correct. So if we have one single task in a brand new environment, then solving the single task is going to be easier than learning the representation of the entire environment. So I think what's interesting about state representation is we're actually learning low-dimensional structures of the environment. And that can be super helpful, for example, if we want to do transfer learning, or if we want to try to use what we have learned before to solve harder and harder problems. But if I have only one single task, then I think a right way to think about this is, for example, if I have a data set and I want to do regression to do prediction, and then the complexity of regression is actually smaller than the complexity of PCA, because regression is really about learning something on one dimensional. Great question, thank you. Okay, thank you very much.